we will look into the chapter haloalkanes and haloarenes. So the general formula of haloalkanes is CnH2n plus 1x. Here n can be the number of carbon atoms. So for example, CH3 CH2x. So here if we take value of n as 2, then and n is 2, H will be 5 and x. So C2H5x. Now we will talk about allylic halides. So these are, in these, sp2 hybridized carbon atom is attached to another carbon which are bonded by double bond. So we can simply say that sp2 hybridized carbon atom is adjacent to a carbon-carbon double bond. Now benzylic halides. So this is a benzene. Here we have a carbon and one halogen. So in these, sp2 hybridized carbon atom is attached to an aromatic ring. So this is how you can represent benzylic halides. Now in the vinylic halides. In the vinylic halides, any sp2 hybridized carbon is attached to the halogen directly. So these are called vinylic halides. And in aryl halides, the halogen is directly attached to the benzene ring. So these are called aryl halides. The what are geminal dihalides and vicinal halides? So geminal are those in which the halogen is present, both the halogens are present on the same carbon atoms, whereas in vicinal ones, the halogens are attached to different carbon atoms. So these are vicinal halides and these are geminal. That's it. So as we know that carbon halogen bond, in these halogens are more electronegative, so they will attract the shared pair of electrons towards themselves. They will have delta negative charge and carbon will have delta positive. So generally we say that halogens have good leaving groups and they will take the shared pair of electron and go away. So the nature of leaving, that is which group will leave faster, will be like this. This is because iodine has a very larger atomic radius than bromine, chlorine and fluorine. So this is an important information. Now we will start with the preparation of haloalkanes. First we will start with preparation of haloalkanes from alcohols. So the first reaction is ROH plus HCl, presence of catalyst thread and Cl2. So basically here what will happen is the OH2 will be removed by Cl. So you can RCl plus H2O water. So this is the first reaction. The next reaction with alcohols is ROH plus NaBr plus H2SO4. This will give us, as we know that this is a reaction for haloalkane, so we will get one haloalkane which is RBr, and we will also get NaHSO4 plus H2O. So this is the second reaction. We will always look for this one because these are not more important. So the third reaction we have ROH plus BX3 gives RX. Here we can write 3RX plus H3PO3. So here we are getting one acid and we can keep this in mind, like here we have 3, so we will write 3H3PO3 3. So we can keep this in mind because we have another reaction similar like this one. So the next reaction we can write ROH plus PCl5 gives RCl plus POCl3 plus HCl. So we can keep this in mind that PCl5, so we get POCl3. So we have to keep this in mind. And the next one is ROH in the presence of red phosphorus and X2, where X2 can be PR2 or IP. So we will get the result as RX. Now the next one is very important because here we can see that two gases are released. So ROH plus SOCl2 gives RCl plus SO2 plus HCl gas. So these two gases are released, and it is very important to remember this reaction because we get special products, that's why. So these were the preparation from preparation of haloalkanes from alcohols. So now we will talk in detail about the Lucas test. We have already seen this reaction of alcohol reacting with HCl in the presence of Z and Cl2 to get a haloalkane. So now we will study what is Lucas test. So it is completely based on this thing. So for this we will take an example of, for example, VCH2OH. We will take primary alcohol. Now what happens here is this primary alcohol has, I will draw it properly again. This O has two lone pairs, and here we have Z and Cl2. Z and Cl2. So what will happen here is this will act, Z and Cl2 will act as a Lewis acid, which will accept the electron pair from oxygen, and so oxygen will get a positive charge because it has donated its lone pair. So it will have a positive charge. So this will be the scenario. CH3CH2OH plus. Now in plus charge oxygen is unstable, so these electrons will be taken by oxygen, and CH3CH2 positive carbocation is formed. Now this carbocation is electron deficient, and also you have to keep in mind that whenever there is a carbocation, rearrangement is possible. So this is a very important point to remember, because in Sn1 reactions carbocations are always formed. So we can also confirm that this is a Sn1 reaction. Now next thing, after the carbocation formation, here HO, Z and Cl2 is formed. Now this, when it will react with this carbocation, here we also have HCl, which is a nucleophile. So here this will attack on this one because this will have positive charge, and this will have negative, as we know that Cl is good leaving group, so it will leave. This will leave and this will get attached here. And this Cl minus will attack on this carbocation. Now as you know, the rearrangement can take place. Here we have only two carbons which are on similar positions, so there is no difference between them, so no rearrangement. But this Cl minus will attack on the positive charge, and we will get the haloalkane. So this is the reaction, and now we will talk about the stability of carbocation, so that we can understand what is the actual test to test the 3 degree, 2 degree and 1 degree carbon, which is primary, secondary or tertiary. So here if we have 1 degree carbon atom, 1 degree carbon atom means it is attached to only one carbon and other are hydrogens. So in this case, as we know that CH3 is an electron donating group, so it will make this step. Now in case of 2 degree, we have two allylic groups, and here one is hydrogen. So we have two CH3s making this step, so it will give it more electrons to make it stable. And subsequently in the 3 degree one, CH3, it will be getting electrons from 3 methyl groups, so it will get more stability. So we can conclude that 3 degree is more stable than 2 degree and 1 degree. So this is the order of stability of carbocation, and this will help us to understand whether the haloalkane getting formed is tertiary, primary or secondary. So now in the 1 degree, 3 degree, we have taken these beakers and we have 1 degree, 2 degree and 3 degree alcohols present. Now then we will add Lucas reagent in all of them. In first one, no reaction, because as we know that in 1 degree carbocation is not that stable, so no reaction. Or you can say that when we heat the solution, the reaction will take place. But in second degree, that is 2 degree, it will take some time to show turbidity. Turbidity means formation of foams, like structure foams. So this we are talking about foams. And in third one, instant reaction takes place and instant turbidity is observed. So this is what is called as Lucas test. Now we will talk about formation of haloalkanes with the help of hydrocarbons. So with the help of hydrocarbons, we can form haloalkanes in the presence of Cl2 and sunlight. So basically what will happen is CH3. So we'll take a basic example of ethane. And here we will Cl2, H will represent sunlight. So here we will have a free radical mechanism in this reaction, but we will write it directly like CH3, CH2, Cl plus HCl. We can write it directly because, I will explain it if anyone won't understand it. So here Cl bond cleavage will take place and two Cl radicals will be formed. Cl radicals, these are called Cl radicals, and after this in the here CH, this will also go and one Cl radical will get attached here. So this is the basic mechanism which you can remember. But the most important thing is this was about symmetric alkane. What if there is an unsymmetric alkane like this one? We'll take this one, for example, propane. So this is propane in the presence of Cl2 and sunlight. We have two carbons for Cl to attach. So Cl can either attach to this one, let us name as 2, and this one. So it will either go on the second carbon or first carbon. It will not go on third one because third and first are similar positions. That's why. So now in this case, we have to follow a rule called Markovnikov's rule. This is Markovnikov's rule in which any protic acid, the electronegative element will always attach to the carbon having lesser number of less hydrogens. So the negative one will attach to less hydrogens. So you can keep this in mind, like negativity wants less hydrogens and positivity wants more hydrogens. You can keep it in mind like that. So if we will apply this harmonic rule, so basically both the products will get formed, but one of them will be major and one of them will be minor, out of which major will be according to harmonic rule. Okay, so here we can see that two products are formed. CH. Like, let me do. So this is one, and this is the second product. So these are two, and out of this will be the major one, because Cl is getting attached to less carbon. Less hydrogen. So this is major and this is minor. So one more thing you can do is the one which is substituted with more carbons, more ethyl groups, will be the major one, and the one which is substituted with less ethyl groups, this is 1 degree and this is 2 degree halide, because it is this C is attached to 2 carbon atoms and this C is attached to only 1 carbon atom. So 1 degree will be minor and 2 degree will be major. So you can understand with this also, or you can use Marconi's rule. Both are also good to go. Now, whenever peroxide, which is represented by H2O2 plus HBr, this reagent is used with alkanes, the reaction changes. That is, it won't have a major change, but it will undergo anti-Marconi's rule, which will be, so we'll take another example. We'll take an alkene plus H2O2 HBr. This is the reagent, and we can write anti-Marconic will get formed. Now, what happens in anti-Marconic is the electronegative one is attached to the more hydrogen one. That is, the carbon having more hydrogens will Br will attach to the carbon with more hydrogens. So this is what is anti-Marconic rule. So in this case, we can see that the Br can attach here and can be attached here as well. On adding simply, we have to break this double bond. One bond we have to break, and one will get H and one will get Br, and the one which is more substituted with hydrogens will be the major product. So the only difference is the major product will get changed. So here we get two products, CH and CH2Br. Sorry, HH. CH3. This is my product, and so anti-Marconic is exactly opposite to Marconic rule. So this will be major over here because Br is attached to carbon substituted with more hydrogen, and here it will be minor because it is attached to lesser one. So this is all about, and this is an exception, you have to keep it in mind. So now we will study about Finkelstein's reaction. So Finkelstein's reaction is also called as halogen exchange reaction. Halogen exchange reaction, and it is performed in the presence of triacetone. So it is a very easy reaction in which the haloalkane is reacted with NaI in the presence of triacetone, which is Ri and NaX. So we can simply say that here halogens are exchanged. So that's all it's about. And the important much to remember about this is it follows Sn2 mechanism, which is one step mechanism. So that's all. Nothing more to remember about this. And also inversion will take place. Inversion will take place here because of back attacking. So we'll take an example of inversion in this case. Easy one. So you can simply take an example about this one. Here, if you have one H on the wedge and one Cl on the dash, and you will react it with sodium iodide and acetone. Acetone can be represented as H3CCH3 double bond O. So nothing will happen actually. Only the H will go on the dash and Cl will come on the Cl. Iodine will come on the wedge because the reaction will take place. So here you will get iodine, and here you will get H, because Cl will be gone with sodium. So here inversion product. So you have to keep in mind that in Finkelstein's reaction, inversion product is formed. That's all. Now we'll study about Schwartz reaction. Now, whenever you will see the name Schwartz reaction, just bring this fluorine in front of you, because this reaction is all about formation of fluorides. So if you take any haloalkane and you react it with AgF, for example, or you can react it with HgF2, Hg2F2, or SbF3, or COF2. Any of this reagent, just you have to remember that any of the haloalkane is taken and it is reacted with any of the compound constituting fluorine, and it will result in the formation of fluoride. That is fluoride and AgCl precipitate, and this is also a Sn2 reaction. So that's all about Schwartz reaction. It is very easy. Just you have to remember that any compound containing fluorine, it will replace the halogen present in the reactant. Okay, so now we will start with Sn2 mechanism. We will study that what is exactly Sn2 mechanism, what are its properties, and etc. So it is, first of all, it is a biomolecular reaction. It is a biomolecular reaction which is second order, and it is one step mechanism. No carbocation is formed in this reaction. No carbocation is formed, and the first step is the RDS, that is the rate determining step. No rearrangement, as no carbocation is formed, no rearrangement will take place, and it is favored by polar aprotic solvents. Now what is polar aprotic and polar protic solvent? So we can polar protic, polar aprotic. So in polar protic solvent, any bond like HO, HF or HN are present, and in polar aprotic solvent, no such bonds are present. Now why these are generally take place in the polar aprotic solvents? Because in general Sn2 reactions have nucleophiles, and nucleophiles lose their nucleophilicity in polar protic solvents. You can understand this when we see the mechanism of the Sn2. It will be very clear that aprotic solvent will favor the Sn2 mechanisms. Strong nucleophiles are involved in the reaction. Strong nucleophiles. Now, as these nucleophiles are strong, that's why polar protic solvents will reduce the nucleophilicity of the strong nucleophiles. That's why generally polar aprotic solvents are used, and here no steric hindrance. There is no aspect of steric hindrance in Sn2. These occur at high temperature. These are very fast reactions, faster than Sn1s, and only one transition state is observed. One state of transition is observed. Now we will study the mechanism of Sn2. So we will take an example of standard mechanism. Also inversion takes place. I think I have mentioned that point. If I have not mentioned, then please mention it. So HO. Now as you know, strong nucleophiles are used. So this is a very strong nucleophile. And here you have one hydrogen over here, H, and one more H. This is on dash, this is on H. Okay. It's methyl chloride, and there is no steric hindrance. That steric hindrance is observed when there are bulky groups like CH3, CH2, etc. Now, as we know that it is a one-step mechanism, so this is the RDS in polar aprotic solvent. So this is the transition state. I will draw it here properly. This C, as we know, this will have delta positive charge. And here OH, delta negative, H. So this will be the case, because as we know that these are strong nucleophiles, so this will attract electrons, and so here Cl will get a delta positive charge. So this is the transition state of Sn2, and the product will be inverted product, as you know, because inversion takes place in Sn2. So inversion will take place in such a way that this will come over here and H and H. So this is called as Walden's inversion. So this was about Sn2, and one more important thing to remember about Sn2 is that reactivity of substrate formed is in this order. Now it has a very obvious reason, because here CH3, CH3X, and here we have just methyl, and methyl. So now this has a very obvious reason, because here the steric hindrance is highest as 3 methyl group are present, and here only 1 methyl group is present. So the attack of the nucleophile will be easier when less steric hindrance. So this is the only reason of this chart. You can keep it in mind. It's very easy. Now one more last thing about Sn2, which is very important, is energy profile diagram. Energy diagram of Sn. Here this is the energy. The y-axis is representing the energy, and this is the reaction coordinate. Here you will have a graph in such a way. These are the products. This is the reactant, and this will be the delta H. This will be the A, and this is the transition state. And here delta H is negative. So it is an exothermic reaction, because delta H is negative, so it is an exothermic reaction. So this was all about Sn2. There is nothing more else. Just keep this diagram in mind, and it's done. In Sn1 reactions, these are unimolecular reactions. These are first order, and steric hindrance affects Sn1. Carbocations are formed. This is the most important point, that carbocations are formed, and a rearrangement is possible. Slow reactions. Sn1 reactions are slow reactions, and the second step is the rate determining step. Over here, these are two-step reactions. No inversion takes place, but racemization takes place. That is, retention and inversion both take place. So these are favored by polar protic solvents. And weak or neutral nucleophiles are used. Low temperature, partial bond formation, and two transition states. So these are all points about Sn1 reaction. Now we will go to the actual mechanism of Sn1. So now we will study about the mechanism of Sn1 reaction mechanism. So as we know that they happen in the presence of weak nucleophile. So this is a weak nucleophile. We have here oxygen is having negative charge and lone pairs, and here we have a reactant with Me represents the methyl group. Here one Me on the dash and another Me on the wedge, and here we have a Br. So in the presence of polar protic solvent, the step 1 that will take place, which is the RTS, is the carbocation formation, in which the transition state is formed in such a way that here is a dash, and here is a wedge, and here is a dash. So no cyclic transition state. The transition state will form. This Br is a good leaving group, will try to break this bond. So this bond will break, and a carbocation will form CH3. And this is a carbocation. So this is the RDS. Formation of carbocation is the RDS for Sn1 mechanism. Now, as the carbocation is formed, in the second step we will look for the products. So this is the most important thing you have to keep in mind. Here, suppose this is a plane, okay, and here is our carbocation. Here is a plane, and this is our carbocation, and here is our nucleophile, which is a weak nucleophile. We can call this as, OCOMe. OCOMe. We can call it as OCOMe. Here is CH3. I'm so sorry. Just a second. Yes, here it is CH3. So we can call it as OCOMe. Okay. So here, this can attack it either from front side or from back side. So now if it will attack from front side, we will get the retention product. Retention product is basically, it will retain its shape. Like here we took the reactant, so here it was Br. So that nucleophile will attach to the side from where the Br has left the molecule. So simply CMe here on a dash, wedge, this is called wedge, and Me, and here OCOMe. So this is the retention of the molecule, and here inversion from left side, it will get attached. So inversion one would be like this. Zoom it. CH3. Methyl will come here. Here another methyl, and OCOMe will get attached on the different side. So these are the two products getting formed in Sn1. So this is all about Sn1 mechanism. Now we will study the energy profile for Sn1 reaction, which is important again. So energy profile, Sn1. As you know that this is the energy coordinate, this is the reaction coordinate, and here for Sn1 it will have two mountains like structures. These are the products, these are the reactants, products. This is the activation energy. This is again the activation energy for the second step. Second transition. This is the first transition, and these are the products, and this is the delta H. Now some basic points to remember is, in Sn1 reactions, generally inversion products are greater in amount than the retention products. That's all.